In this video, we're going to analyze false and true colored images. Here we're going to use the Crab Nebula as our example. And we have 6 different images of the Crab Nebula based on 6 different wavelength bands. We have the radio band on the left, the infrared band next, the visual wavelength band next, then the ultraviolet band next, finally the X-ray band, and last would be the gamma ray band. So what we have is increasing energy to the right. So the gamma ray is at a higher energy than the radio. So when looking at gamma rays, we're looking at where in the Crab Nebula of the surface is emitting most of this gamma ray light. And if we look, we see it's mostly concentrated in the center. When you look in the visual wavelength band has a larger surface area. The object's surface is emitting much visible light. Compare that with the X-ray band and the gamma ray band. You don't have all that extended area in the field of view emitting X-rays or gamma rays. You find gamma rays and X-rays concentrated more towards the center of the Crab Nebula. Now let's concentrate on the visual wavelength band. Out of all of the images that we're looking at in different wavelength bands, the visual wavelength band is the only one that's a true color image. All the rest of them are false colored images. What this means is you could go to the Crab Nebula and take a photo of it, and this is what you would see in the visual wavelength band. But if you tried to look at the visual wavelength band in radio waves, you wouldn't see anything. Your eyes don't see radio waves. You would see just the color black for radio waves. Your eyes can't see sound waves passing through the air around you. You hear it, but you can't see it. So that's an example of radio waves that you can't see. So we take images of objects in different wavelength bands, and then we falsely color the image so we can analyze it. And so you see that we falsely colored the images with reds and yellows and greens and blues, just so we can analyze where is most of the radio light compared to less radio light. And wherever you see black is no radio light. Same thing with the infrared. If you look in the infrared, your eyes can't see infrared. You can't see heat, but you can feel heat. So since you can't see heat, your eyes would only see black for infrared in the image. So we take an image of the Crab Nebula in infrared, and then we falsely color it where we see higher concentrations of infrared compared to lower concentrations. Same thing with the ultraviolet, X-ray, and gamma ray band. Now, to understand the true emitted colors by the objects in the visual wavelength band, you need to understand the rainbow of colors related to temperature and energy. So let's do a little sidestep. Go look at the rainbow of colors and black and white. So if you look at the rainbow of colors, you've got your red, orange, yellow, green, blue, indigo, and violet. Now, objects that emit visual light will emit these rainbow of colors, but sometimes you also see red, orange, yellow, green, white, blue, indigo, violet, and of course black. Sometimes the images have all of the colors of the rainbow plus white and black. Now, white is a blend of all the colors. You blend the Roy G. Biv of colors together, you get the color white. You separate white light out into red, orange, yellow, green, blue, indigo, violet. So I put this white band in the center of the rainbow of colors so you can see that it's a mixture or a blend of the rainbow. I put black on either side of the rainbow of colors because you can't see in the infrared or you can't see in the radio band. So black would be on the other side of the red color where infrared and radio band is of the V band, compared to the V band, that is. Same thing on the other side of violet. In the ultraviolet, you can't see, your eyes can't see in the X-ray band, and your eyes can't see in the gamma ray band. So you would see the color black for these bands. Energy is going to once again increase to the right. It's also in the same direction as temperature. And we're looking at the surface temperature of the object. So in the visual wavelength band, if you see red, that's going to be a cooler surface than where you see blue or violet. So let's go up and take a look at the visual wavelength band of the Crab Nebula. Notice that you see some reds and oranges and yellows, but in the center region you might see whites and these greens. So wherever you see greens and whites, those are higher temperatures, higher energies than where you see the reds, the oranges, and the yellows. And that is a true color image. Now you can see in the true color image, in the visual wavelength band, where the hot colors are, which is blue and violet, compared to where the cooler surfaces are, which is red and orange and yellow. Now let's compare that with the radio band. We know that the highest energy is in the center, but notice in this falsely colored image, they colored the center red. We know that red is a lower energy and a cooler temperature in the visual wavelength band. So this particular author decided to falsely color the image where red is going to be a hot color and blue is going to be a cooler color. And they did this for the general public because the general public thinks of blue, like blue water, as a cooler color, and hot, red, like a red hot, as being hot. So they falsely color this image for the public to be presented on a news station or in a newspaper, where red is going to be the hot colors and blue is going to be the cool colors. If it was an image that was going to be for a scientist, it would be colored the other way. It would be colored with blue in the center and red on the outside. So we know when we look at this radio image, it's falsely colored, and they falsely colored it for the public. Let's go and take a look at the visual wavelength band compared to the infrared band, and let's see how they falsely colored the infrared band. Here I zoomed in, and notice in the infrared, they pretty much kept to two colors. They have a gray scale, and they have this pink to red color. So this gray scale, if you look, is like a white to gray, and if you look, you see these red regions. So let's compare it with the visual wavelength. We can line these filaments up with these filaments in the visual wavelength band. In the visual wavelength band, we see them as whites, and in the infrared band, we see them as red. In the visual wavelength band, we see these outer regions as going to be this white, this in the visible light, we see it as these yellows, and in the infrared, we see it as these whites to grays. So we know in the visual wavelength band that the oranges are the cooler colors. So we know that they colored this one, even though it's falsely colored. So we'll put an F here for falsely colored and a T for true color for the visible light, falsely colored for the infrared. We know in the falsely colored image where they put the red filaments that that is going to be a cool color. And you compare that where the other regions, the whites to the grays to the blues, that's going to be more of a hot color in this infrared comparison. Now let's compare the same visible light, but with the ultraviolet light. So in the visible light, we have the true colored image, and in the ultraviolet light, we have the false colored image. And they just have combinations of whites and grays. It's once again a grayscale, where we have the highest concentration of white in the center and the least concentration in the outside. Now, if you look in the visual wavelength band, we see some oranges and reds in the center, and then we see these blues and greens to oranges and reds in the outside. So this ultraviolet region, they have the center is going to be the hot. So the deepest white area is going to be the hot region. And then you have this falsely colored gray on the outside, and that's going to be our cooler region. Now let's go back up and compare the ultraviolet with the X-ray and the gamma ray to the visual wavelength. Let's start with the X-ray. Notice the X-ray has blues and whites in their colors. The white is comparing with the ultraviolet, where the deepest white is, and you don't really see anything in the center of the visible light that compares with the X-ray image. The X-ray image is showing us where the hotter regions are, so where you see white is going to be hot, and where you see blue is going to be cool. So since blue is really a hotter color than white, this falsely colored image is for the general public. Now let's go take a look at the gamma ray. In the center, we notice that they have it more of white to yellow, and in the outside, we have it more of red. So the red colors are going to be the cool, but they put in the center is going to be the hot color. So this image in the gamma ray band is colored for the scientist, where the reds are the cool colors and the whites are going to be the hot colors. So when you take a look at images, you have to keep in mind that the images are going to be falsely colored, either in a grayscale or a color scale. And in the color scale, either red will be hot or red will be cold, and the opposite end will be true. So if red is hot, blue is cold. Or if red is cold, then blue is hot. One set of falsely colored images is for the public. One set of falsely colored images is for the scientist. If it's for the public, red will be a cool color, blue will be a hot color. If it is for the scientist, then you will have red as a cool color and white to blues as a hot color. This is how you analyze false and true colored images.